Hi, it's great to be asked to give this talk by the Edinburgh Science Festival. Obviously, I would have preferred to have been in Edinburgh, one of my favourite cities, but thanks to the wonders of modern technology, I'm talking to you from my living room in central London. To get me in the mood, though, and to make me feel as if I'm in Scotland, I've actually got this wonderful knitted Nessie that I bought in Edinburgh last year. So rather than talking to nobody, I shall talk to this lovely stuffed animal. I want to talk about the subject matter of my new book, The Magicians. So here goes. Antarctica was discovered by people who went out in ships and discovered it. But Neptune was discovered by a man sitting at a desk in Paris with a quill pen. And this, I think, illustrates the central magic of science. That it's possible to write down a mathematical formula on a piece of paper, on a blackboard, on a whiteboard, and it can predict the existence of things previously not suspected, that when people go and look, they actually find they exist in the real world. Now, this magic is so magical, so miraculous, that even the scientists themselves can scarcely believe it. So famously, Einstein did not believe two predictions of his own theory of gravity: black holes and the Big Bang. Anyway, what I'd like to do today is to give you some examples of scientists who demonstrated the central magic of science, and then finish by speculating on why this magic works. But first of all, I just want to tell you what science does. 3.6 million years ago, three of our ancestors walked across a bed of freshly fallen volcanic dust, and they left their footprints there. And those footprints can be seen at Laetoli in Tanzania today. And they're intensely evocative. You immediately wonder, who were these three individuals? How were they related to each other? And what was their mission on that day, tens of thousands of centuries before the birth of civilization? Well, of course, we'll never know the answer to any of those questions. However, we can speculate about the thought processes of those ancient humans. They lived in a chaotic and unpredictable world just like us. But they would have noticed that some things are predictable. So, for instance, the sun comes up once every day, the moon goes through its phases every 28 days, and the seasons roll on year after year. But probably they didn't speculate beyond that. So fast forward to 3000 BC and an incredibly important invention, writing. It arose apparently simultaneously in Sumeria, which is modern-day Iraq, and Egypt, although there are some hints that the Egyptian form came first. Now, with writing, it was possible to record what you saw in the sky. And you could assemble those recordings for months or years and discern very subtle patterns. And so people were able to predict the existence or predict spectacular celestial events like total eclipse of the sun, total eclipse of the sun, when the moon moves across the sun, blots it out, and the world is plunged into darkness at midday. And of course, anyone who could make that prediction would strike awe into the populace, and this gave immense power to the scribes and the kings and the emperors who could make these predictions. But that power is nothing compared to the power of science, which arose in the 17th century. Because what science does is it finds the laws, the deep laws, which underpin the patterns and which explain the patterns. And those laws, the most important thing is they are portable. So, for instance, Newton's law of universal gravity, he deduced from observations of the planets and from the moon in particular. But he could then use that law of gravity in an entirely different domain to explain why there are two tides in the ocean every 25 hours. And those laws are also mathematical. That's an important thing. They can be written down as a mathematical formula, and they have immense predictive power. So I'm going to go to my first magician, and he is the man who did predict the existence of the planet Neptune. His name was Urbain Le Verrier, and he was an astronomer in the mid-19th century in Paris. And he was very interested in the planet Uranus, or Uranus, however you like to pronounce it, which had been discovered by William Herschel in 1781. Now, William Herschel was a freelance German musician who had moved to Bath from Hanover in the mid-18th century, and he'd come with his sister Caroline, who was also an astronomer, and incidentally discovered more comets than any other woman in history apart from Caroline Shoemaker, another Caroline who lives today. Well, Herschel got himself a job as a church organist in Bath, but his real passion was astronomy. And in his garden in Bath, he constructed some of the best telescopes of the day. And with those telescopes, using one of those telescopes, on the 13th of March 1781, he spotted this kind of fuzzy disk in his viewfinder. At first he thought it was a comet, but over the next few days, as he followed it, as he observed it, he realised it wasn't following the orbit of a comet, it was following the orbit of a planet. A discovery of Uranus was a sensation because overnight it doubled the size of the solar system. It was twice as far away from the Sun as Saturn, which was the outermost planet at the time. And it was also the first planet discovered in the age of the telescope, and the first planet that was unknown to the ancients. So it's unknown to the Babylonians, the Greeks, the Egyptians, all these people, they didn't know about it. But the minute it was discovered, it was realised it had been seen before. In fact, it's been seen about a century before by John Flamsteed, who was a contemporary of Newton's. He hadn't recognised it as a planet, of course, so there was 100 years of records of this planet. So it was quite easy to calculate its orbit. But there was a problem. Whenever you calculated the orbit of this planet, and it predicted the orbit where it would be in a month or 2 months or 3 months, it was never where it was predicted to be. And it was Le Verrier in Paris who suspected that there was another planet even further from the Sun, from Uranus, and that its gravity was tugging on Uranus and perturbing its orbit. And he set out to try and predict where that planet would be found. Now, this is a tremendously complex problem to solve, because the problem with Newton's law of universal gravity is that it's universal. In other words, there's a gravitational pull between every chunk of matter and every other chunk of matter. Well, what this means is that Uranus is not just pulled by the gravity of the Sun, it's pulled by the gravity of the Earth, Jupiter, Saturn, every planet in the solar system. So the problem that Le Verrier had to tackle was how to subtract the effect of all these other planets on Uranus so that he would be left with the pull of this hypothetical planet. But finally he managed to do this calculation, and he predicted that the new planet would be found, if anybody looked, between the constellation of Capricorn, that's the goat, and Aquarius, the water carrier. So excited, he went to the director of the Paris Observatory, a man called François Arago, and said, "Can we look for this planet?" And he was told immediately, no. This wasn't actually very surprising, because it turned out that national observatories existed, so Greenwich and Paris, they existed to record the positions accurately of stars for navigational purposes. This took a lot of manpower, and Arago did not want to give over any of that manpower for a search for a hypothetical planet. You've got to remember that no one in the history of the world had ever predicted the existence of a new planet. So it seemed like a wild goose chase to Arago. So Leverrier was very, very frustrated. But then he had an idea. He thought he would write to an astronomer in Europe who was a lowly astronomer, and therefore someone who wanted to make their name, and ask them if they could look for the planet, because they would be highly motivated. And suddenly he remembered that a year before he'd had a letter from a man called Johann Gaul at the Berlin Observatory, and Gaul had sent Leverrier, he'd sent him his thesis, and Leverrier was quite an arrogant man, and he'd not replied to Gaul. But suddenly he got very friendly. He wrote back to Gaul, said his thesis was wonderful, and said would he look for this planet. Well, Gaul was intrigued, and he went to the directorate of the Berlin Observatory. But of course he got a very similar reaction to the one that Leverrier had got in Paris. However, Gaul had a piece of luck, because the director of the observatory, a man called Johann Encke, it was his 55th birthday, and he was having a birthday party. So because of that, he wouldn't be using the giant Fraunhofer refractor at the Berlin Observatory, which was one of the best telescopes in the world. So, incredibly, Gaul got to use it. And with an assistant, Heinrich d'Arrest, they started looking for the planet at midnight on the 23rd of September 1847. And within an hour, they found the planet. They found what we now call Neptune. It was the outermost planet. And this discovery was a sensation of a different order to the discovery of Uranus, because Uranus had been discovered by Herschel. He'd stumbled on it by accident. But Neptune had, as I say, been predicted by a man sitting at a desk in Paris with a quill pen. So, first of all, it demonstrated the power of Newton's law of gravity. Not only could it explain the things that we could see, it could predict the things that we couldn't see. But more than this, it really did emphasize this central magic of science, that it was possible to write down a formula that would predict the existence of things no one had ever suspected that turn out to be real. So it was such a sensational discovery that Leverrier was courted by kings and queens all across Europe. He was a superstar of science because he demonstrated the power of science. And it was he really liked the fame, and he liked the attention, and he wanted more of it. So he thought to himself, I've looked at the outer solar system, why don't I look at the inner solar system and see if there's a planet that is moving in a way different from the way it should. And incredibly there was. The planet Mercury, the innermost planet, was not moving as Newton's law of gravity predicted. So Leverrier proposed that there was yet another planet closer to the Sun than Mercury, which was the closest planet to the Sun, and he called it Vulcan. And for 50 years afterwards, people looked for Vulcan, and some astronomers found it and some didn't find it. But it turned out it was an illusion, because incredibly there was a different reason for the perturbation of the outermost planet to the perturbation of the innermost planet. In the case of the outermost planet, it was the existence of a new planet tugging on it, but in the case of Mercury, the innermost planet, Newton's law of gravity was incorrect. And in 1915, Albert Einstein came up with a better theory, the general theory of relativity, and was able to predict correctly the orbit of Mercury. But Vulcan still exists, or still survives, as the home world of Mr. Spock from the Star Trek TV series. Okay, so my next magician is somebody relevant to Scotland and Edinburgh in particular. His name is James Clerk Maxwell. He went to school in Edinburgh, but he had a quite sad childhood. His mother had died when he was 8. She died aged 47 of stomach cancer, exactly the same cancer that would kill Maxwell at exactly the same age. And because his mother had died young, he was brought up by his father at their estate Glenlair near Dumfries. And his father wasn't really very good at dressing him, and he was dressed in kind of country clothes. So when he came to sophisticated Edinburgh and he went to school, he was ribbed and bullied by the other boys because of his clothing, and they nicknamed him Dafty, which is a pretty ironic when you consider that he would turn out to be the most important physicist between the age of Newton and Einstein. Now, Maxwell went on from Edinburgh to Cambridge, to Trinity College, and when he got his first degree, he wanted to do research. He wanted to understand electricity and magnetism. These were the kind of buzz subjects of the day. In 1781, Luigi Galvani had actually twitched a frog's leg, a dead frog's leg, with electricity. And so electricity was seen as satanic even, because you could animate dead things with it. And, well, of course, that led to Frankenstein being written by Mary Shelley in 1818. And there was a connection between electricity and magnetism that had been found by a Danish physicist. So this was all a big mystery, and no one had any idea what electricity and magnetism were. So what Maxwell did was he wrote to a family friend, William Thomson, another Scot, who would be called Lord Kelvin, and would be responsible for laying the first telegraph cable between Britain and America. And he asked William Thomson who he should read to basically learn all he could about electricity. And Thomson said, read the work of Michael Faraday. Now, Michael Faraday's life was as different from Maxwell's as it was possible to imagine. He was the son of a poor blacksmith in Marylebone, which is where I'm actually giving this talk from. And he was apprenticed to a bookbinder when he was 14. The bookbinder was a Huguenot refugee, and he encouraged the young Faraday to read the books that he was binding, and many of them were scientific. So actually Faraday educated himself. He was self-educated. And then one day a miracle happened. A man came in to the bookbinders with a spare ticket for a series of lectures by Humphrey Davy. Now, Humphrey Davy was probably the most famous physicist or famous chemist of his day. He was so famous, he discovered many elements. He was so famous that Napoleon gave him an award even when Britain was at war with France. And not only was he a great scientist, but he was a great performer as well. And he gave very, very animated lectures. In fact, women would actually faint in his lectures. Anyway, the bookbinder gave the ticket to Faraday and said, you go to those lectures. And really, the ticket that Faraday got was pretty much like the golden ticket that Charlie gets in Charlie and the Chocolate Factory, because eventually it would change his life. So Faraday went to Davy's lectures at the Royal Institution in Piccadilly, and he made incredibly detailed notes which he illustrated, and later he actually sent them to Davy. Davy was incredibly impressed and wanted to employ Faraday, but he had no jobs. And poor old Faraday really was succumbed to gloom and thought that he would spend his whole life bookbinding. But actually, many months later, Davy's assistant was caught fighting and was fired. And Davy wrote to Faraday and said, would you like a job? And Faraday became his bottle washer, then his assistant, and when Davy died, he became president of the Royal Institution. So in the end, although Davy was this great scientist, his greatest discovery would turn out to be Michael Faraday. So Faraday really had no mathematical background, but he had great intuition, and he could visualize magnetism and electricity. So he would hold two magnets close together and he would feel the force between them. And he was convinced there was something in the air, in the space between the magnets, which was pushing them apart. And so he concocted the idea of a thing called a magnetic field, a magnetic force field, which emanated from a magnet and which was felt by the second magnet. And around, for instance, a conducting wire, there was kind of a tornado, a tornado of magnetic force. So he really had this visual image of the empty space being filled with magnetic and electric fields. And this meant that he did experiments that nobody else would think of doing. And this culminated in 1831 in Faraday constructing in his basement laboratory the world's first electric motor, which used this kind of tornado of magnetic force to drive a motor. And it was whirring around. He was there with his 14-year-old nephew, and they danced around the table because they were so jubilant. And what an incredible sight that must have been, because outside on the street there were horses and horse-drawn carts clattering across the cobbles, and this whirring electric motor, the only one in the world, must have felt like to us now, it seems like a piece of the 20th century that had somehow fallen through a crack of time and ended up in the Victorian era. Faraday went away with his nephew and they celebrated at a circus. But this idea of magnetic fields was heretical, and other scientists of the day humiliated Faraday for it, because the god of science was Newton, and Newton had explained gravity as a force at a distance. So gravity between the sun and the earth was a force which operated with no medium between, no mediator between the sun and the earth. But Faraday was saying that the magnetic force was mediated by this magnetic field. And so he was humiliated, and people knew that he had no mathematical ability. But then, one day he received a letter from James Clerk Maxwell. And when he opened it, it nearly brought him to tears, because James Clerk Maxwell said he believed in the magnetic field. He believed that it was a real thing. And Faraday knew that Maxwell was a Cambridge-educated mathematical physicist, and it was incredible to get that seal of approval. And they would become kindred spirits, even though Faraday was 40 years Maxwell's senior. So the problem that Maxwell had was to turn Faraday's pictorial idea of magnetic fields, filling all of space, swirling, and into something mathematical. And he succeeded in doing that. It took him quite a while, but he started with a model. This is what scientists always do. They try and create an everyday model of the phenomenon. So how does a magnet affect or pull on a piece of metal across empty space? Well, Maxwell imagined that all of the empty space in the universe was filled with tiny, invisible, toothed cogs, which could turn. And so he imagined that a magnet turned a cog in contact with it, which turned another cog, and eventually transmitted the force to a piece of metal. And he had to keep tweaking this model because, for instance, to make it mesh with reality. So it was known that the magnetic force was intensified. It became stronger in a metal like iron. So Maxwell had to make the cogs move more easily in iron. He had to make them springy. In fact, he had to tweak his model so much that eventually he threw up his hands in despair and realised that the only way to describe magnetic and electric fields was mathematically. So this was a seismic shift in physics. This was the first time someone had realised that the deep fundamental world beneath the skin of reality is not like anything in the everyday world, and it can only be described mathematically. Well, Maxwell ended up with Maxwell's equations of electromagnetism, 4 of them. They're so famous today that physics students often wear them on their t-shirts. However, what few people realise is that Maxwell had 20 of these equations, and the 4 that most people know were actually, the 12 were condensed into 4 by another physicist called Oliver Heaviside. So If you fiddle with Maxwell's equations, and he did, it's very easy to create a wave equation. And Maxwell did this, and it described a wave in the electric and magnetic fields, rather like a ripple going across the surface of a pond, a ripple in the electromagnetic fields. And his theory gave the speed of that electromagnetic wave. It depended on two numbers, and at the time, Maxwell didn't have access to those numbers because he was on holiday in the summer at Glenlair with his wife Catherine. At the time, he was a professor of physics at King's College in London. So he knew that the numbers he needed had been measured by German physicists and were in a textbook in the library at King's College. So he had to wait until the summer was over. He came down on a train with Catherine. She brought her pony, Charlie, with her because Maxwell and his wife used to ride their horses in Hyde Park in central London. They got to London. They were living in a house which was in Kensington on the far side of Kensington Palace, where Prince William and Kate live now. And Maxwell had to travel 4.5 miles on a horse-drawn omnibus into King's College. He did so. When he got there, he rushed to the library. He found the textbook he needed. He plugged in the numbers into his theory, and he found, to his amazement, that the speed of an electromagnetic wave was the speed of light. So for the first time in history, someone had realised there was a connection between electricity and magnetism and light. Light was a wave in the electromagnetic fields that permeate all of space. And he realised also that when we see a rainbow with its colours going from red to violet, what we are seeing is different vibrations of the electromagnetic wave. So a red corresponds to a very sluggishly vibrating or oscillating electromagnetic wave, and violet to a much faster oscillating wave. And as he left King's College that day and he stepped out into the Strand, it would have been really busy with horses and horse-drawn carts and costermongers, and he realised something else, and that was that his theory placed no restriction whatsoever on how fast the electromagnetic waves could oscillate. So it was possible to have waves which oscillated more sluggishly than red light and more quickly than violet light. In fact, there could be millions of invisible colours in addition to the 7 in the rainbow. So he was the first person to realise that the universe was probably awash with these electromagnetic waves, none of which we had known about, none of which we could sense. And everything came from the prediction of Maxwell's equations. So something that no one had previously suspected had been predicted. But of course he never got to prove this because unfortunately he died aged 47. But 16 years later, in Karlsruhe in Germany, there was a physicist called Heinrich Hertz. And Heinrich Hertz, on his laboratory table, set up a transmitter. He didn't call it a transmitter, but we would call it a transmitter today. And basically it was a high voltage source which created an oscillating spark in a spark gap in a circuit. And 1.5 meters across his laboratory desk, he had a circle of wire with a tiny gap in it. We would call that a receiver. And when he created this stuttering spark in his transmitter, there was an answering spark in the receiver. Something had actually travelled 1.55 metres through empty space across his laboratory table and created a second spark. And he realised that it was an invisible electromagnetic wave predicted by James Clerk Maxwell. And we now call those waves radio waves. When asked whether he thought they were important, he said they were of no importance whatsoever, which is pretty incredible given that Heinrich Hertz effectively invented the 20th and 21st centuries, and we owe our entire ultra-connected world to Heinrich Hertz. So, My next magician is Karl Schwarzschild. Now, Karl Schwarzschild was a German. He was actually the director of the Berlin Observatory when war was declared, the First World War was declared. He immediately signed up to join the German army, which was an unusual thing because he was 40 years old. But he was partly Jewish. He wasn't a practicing Jew, but anti-Semitism was on the rise in Germany. And he joined up because he wanted to show that a Jewish German was as patriotic as anyone else. And Schwarzschild ended up working, or actually calculating, artillery trajectories with an artillery battery in France. And then he worked with a weather station in Berlin. But in the early winter of 1916, he developed blisters in his mouth. He didn't really think much more of it, but the blisters spread to his entire body. They were weeping, bleeding blisters. And he ended up in a field hospital on the Eastern Front, on the Russian front. And the doctors really didn't have any idea what it was for quite a while, but eventually they diagnosed a disease called pemphigus vulgaris, which has no cure even today, although it can be treated with steroids. And it's a disease in which the immune system actually attacks your skin. Now, Schwarzschild knew this was very serious because your skin is your biggest organ. And really, if it's compromised, then you're open to microorganisms and to infection, so you can die of an infection. But also, your skin is the means by which you get rid of heat. And so if it's compromised, you can overheat. So he knew it was very, very serious. But lying in his hospital bed on the Eastern Front, he tried to distract himself with physics. And when he was in Berlin, he knew that Albert Einstein was developing a new theory of gravity. He didn't know Einstein very well, although he actually said hello to him in passing. But he knew that Einstein was developing this theory. And he heard that Einstein had presented this new theory of gravity, general relativity, in 4 lectures at the Prussian Academy in November 1916. And within a couple of weeks, he was able to get copies of, or summaries of those lectures in his hospital bed. And he devoured them. Now, Newton had thought that there was a force of gravity between the sun and the earth, rather like an invisible tether. And so, and it was that tether that constrained the earth to circle forever around the sun. But Einstein realized this was incorrect. What the sun actually does is create a valley in the space-time around it. We can't see it because it's a 4-dimensional thing, and that's why it took the genius of Einstein to realize it. But the earth, there is no force of gravity. The earth is just traveling along the only path it possibly can, around the upper slopes of the valley of space-time around the sun, rather like a roulette ball in a roulette wheel. Now, the problem with the theory, what you needed to do was you needed to work out the warpage or curvature of space-time for any particular mass, because warpage of space-time was gravity. That's what gravity was. But this was incredibly difficult. Whereas Newton had one formula describing gravity, Einstein had 10. So Einstein thought it would be impossible to get what we call a solution to his theory. It would be impossible to find an exact description of the space-time curvature around any given mass. And so he'd used an approximation, and he'd used the approximation to successfully predict the motion of Mercury, or explain the motion of Mercury. But lying in his hospital bed on the Eastern Front, Schwarzschild was sure that he could do better. And incredibly, he was able to do it. He found an exact solution for the curvature of space-time around a compact mass like the Sun. And he wrote it up as a paper and he sent it to Berlin. And Einstein opened this paper, this envelope. He was incredibly surprised to get a letter from the Eastern Front. And when he opened it, he was even more surprised, because there was something he thought was impossible, this exact solution to the curvature of space-time around the Sun. And he was so impressed he wrote back to Schwarzschild, and he later presented, the following week, he presented Schwarzschild's paper at the Prussian Academy of Sciences. But Schwarzschild had not finished. He had worked out the curvature of the space-time outside a body like the Sun, used it, for instance, to predict the motion of Mercury. For his next trick, he decided to work out the curvature inside. And he discovered something amazing. If the mass were compressed really small, the curvature of space-time would get steeper and steeper. The valley would get steeper and steeper until eventually it became a bottomless pit from which nothing, not even light, would escape. A monstrous body. Now, he had no word for this body. In fact, the word would not be coined until 1967 by John Wheeler, the American physicist. But pretty much everybody on planet Earth knows the name of this body. It's a black hole. He sent his paper on black holes to Einstein. Einstein duly presented it at the Prussian Academy, but he never believed in black holes. He thought they were too monstrous to be true. And he thought that eventually there must be some force in nature which would prevent a body from collapsing down to form a black hole. So we now fast forward 50 years to a 15th century castle. Please excuse the lorry going past outside. To a 15th century castle in East Sussex, Herschel Castle. This was the home of the Royal Greenwich Observatory, and in a turret room there was a young astronomer called Paul Merdin. So this is 1971. And he had been working in America for 7 years doing his PhD and his postdoctoral work. And he'd come to the Royal Greenwich Observatory. He had a young family, but he didn't have a permanent job. So he really wanted a permanent job. He needed to make his name to get a permanent job. Now, when he'd been in America, he and the other graduate students had often discussed how you would find an interesting object in astronomy. This is the problem in astronomy. There are 2 trillion galaxies, each with like 100 billion stars. How do you find an interesting object? It's kind of like finding an interesting sand grain among all the sand grains on all the beaches on Earth. And while he was in America, he thought that maybe if an object was giving out X-rays, it would be kind of like waving a flag saying, look at me, look at me. Because X-rays are produced by matter when it's heated to hundreds of thousands or even millions of degrees, so very extreme. So it turned out that people had begun X-ray astronomy in the early 1960s. The Earth's atmosphere, fortunately for us, screens out X-rays. So you have to go above the atmosphere to observe them from space. And an American called Ricardo Giacconi had used sounding rockets. These just went up in the air straight up and came back down again, carrying X-ray telescopes to get brief glimpses of the X-ray universe. And a number of sources had been discovered. Among them was an object called Cygnus X1. Now, maybe the fact that it's called Cygnus X1 tells you that the telescopes were very crude and they were unable to say where it was in the constellation of Cygnus. They just really they weren't able to see detail in the sky at that time. Now, just before Merdin came back to Herschel Castle from America, the first X-ray satellite had been launched. It was called Uhuru. It was launched by NASA. And when he was back at Herschel, Merdin got a copy of the catalogue of objects, and he quickly looked for Cygnus X1. And he found that the box showing its location had shrunk now. It didn't fill an entire constellation, it was much smaller. So he looked within that box to see if there was an interesting object. And there was one. It was a blue supergiant star. So this is a star maybe 20, 30, 40 times the mass of the Sun, pumping out hundreds of thousands of times as much light as the Sun. So that to Merdin seemed like an unusual object. But he knew that an ordinary star could not produce X-rays. It could not generate the temperatures of millions of degrees which were needed. So the question was, did this supergiant star have a companion, which was the source of the X-rays? Now, sharing his office at Herschel was a woman called Louise Webster. She was about the same age, 30. She was an Australian. Unfortunately, she would have a very pretty much sad life, and she would have the first liver transplant in Australia, and would unfortunately die young. But she was working on a project with Richard Woolley, who was the director of the Royal Greenwich Observatory, basically to work out the motion of stars in our galaxy, in our Milky Way. And this involved exploiting something known as the Doppler effect. So if you hear a police car coming towards you, you know it's got a higher pitch. If it's going away from you, it has a lower pitch. Well, and exactly the same thing happens with light. When an object's coming towards you, the light has a higher pitch. It becomes shifted, what we took to the blue end of the spectrum. We call it a blue shift. And when it's moving away, it's got a lower pitch and it becomes redshifted. So this was the way to determine whether the blue supergiant star had a companion. Because if it was moving towards us and away from us in its orbit, we'd be able to detect that as a Doppler shift. So Merdin gave the coordinates of this supergiant star to Louise Webster. She was using the 100-inch telescope at Herschel, which at the time was one of the biggest telescopes in the world. It had been built in the most stupid location possible because it was always cloudy. It would eventually be moved to the Canary Islands, and it would cost more to move it and reconstruct it than it did to actually build it in the first place. Well, very quickly, Louise Webster found that the blue supergiant star was indeed orbiting something every 5.6 days. And they sat down, the pair of them, in their office, in this turret room, in this 15th century castle, to discuss what it was orbiting. Their calculations showed that if it was being swung around every 5.6 days, the object swinging around had to have a mass of at least 4 times the mass of the Sun, and possibly more than 6 times the mass of the Sun. So what could the object be? Because it was invisible. The blue supergiant star was orbiting an invisible object. Well, there are only a few candidates. The first kind of compact object was a white dwarf. This is kind of the end point of the evolution of a star like the Sun. It's the star's future. It's the Sun's future. So a white dwarf is about the size of the Earth and very, very faint. So it would be invisible. But there is a limit to the size of a white dwarf. It's about 1.5 times the mass of the Sun. But of course, this invisible object that Merdin and Webster had found was more than 4 times the mass of the Sun. So what else could it be? Well, there was one other object, and that was a neutron star, which had been discovered by a graduate student at Cambridge, Jocelyn Bell, about 4 years earlier, in the guise of what we call a pulsar. Now, these stars are even more compact. They're about the size of Mount Everest, and they're also incredibly faint. But they too have a limit on their mass. It's very hard to get a star more than about twice the mass of the Sun. So really all the candidates were ruled out except one. And Webster and Merdin exchanged glances, and they both realised that the invisible object had to be the object that had been imagined by a man dying of an agonising skin disease in a World War I field hospital half a century before. It had to be a black hole. Now, this was a tremendous discovery, so you'd think that it would be easy to get this published. However, it turned out that to publish a paper, they needed the approval of Richard Woolley, who was the director of the observatory. And until a few years before, the observatory had been run by the Navy, and the Navy was incredibly conservative. So Woolley didn't want to get egg on his face. If this was a mistake, he didn't want to be humiliated. So he dragged his feet, and it took a long time before he allowed Merdin and Webster to send their paper to the journal Nature. And it was published, and Merdin got his wish. He got a full-time job. He also got a bigger house, so he was the first person in history to have his mortgage paid by a black hole. And to celebrate, he took his wife and his 2 children, his 2 boys, 2 and 5, to a beachfront cafe in Hastings, and they celebrated by eating Knickerbocker glories. And presumably his sons hoped that their father would find more black holes. But what an incredible contrast. The man who predicts the existence of black holes is dying in a field hospital in World War I, and the man who finds them, or is the co-discoverer of black holes, celebrates with ice cream sundaes in a beachfront cafe at an English seaside resort. Anyway, black holes turn out to be very common. Einstein was completely and utterly wrong. Only about a dozen or so are known in our galaxy, the Milky Way, but every single galaxy has a supermassive black hole in its heart. No one knows why. They range in mass from ones which are about 30 billion times the mass of the Sun, down to ones which are tiny tiddlers like our one, which is only 4 million times the mass of the Sun. No one has the slightest idea what they're doing in the centre of galaxies. Nobody knows, for instance, whether they were there first, and whether they were the seeds about which galaxies formed, or whether galaxies formed and maybe dense clusters of stars collapsed to form the black holes. The origin of the supermassive black holes in galaxies is one of the big unanswered questions in cosmology. But there was a major development last April, when we got the first ever image of a black hole. It was an image of the black hole in the heart of M87, which is a nearby galaxy. It's a 7 billion solar mass black hole. The image was obtained by a global array of radio dishes called the Event Horizon Telescope. Harnessed together, they were effectively a telescope the size of the Earth. And the bigger the telescope, the finer the detail you can see. If you saw this image in the media, maybe you were underwhelmed by it because it just appeared to be a kind of orange halo around a circular black void. But I think this image is one of the most important images in the history of science, to rank alongside the image of the Earth rising above the moon, or the DNA spiral of the spiral of DNA. And you need to understand this image. The actual void is about the size of our solar system. That's the size of the black hole. And the donut of light around it is matter superheated as it falls into the black hole. And when it crosses over the edge into the black void through what we call the event horizon, the point of no return for infalling matter and light, it's never seen again. It's never seen again in our universe. And in the heart of the black hole, space and time, we believe, are ripped apart. So it's very easy to, as human beings, to beat ourselves up and think that we do terrible things to the planet, greenhouse warming and pollution and overcrowding and all kinds of stuff. But I think sometimes we should pat ourselves on the back, because we are a jumped up ape that evolved on an African plain 3 or 4 million years ago. We have a brain that weighs about 3 pounds and is mostly jelly and water, yet we have seen to the very edge of space and time. Well, why does this magic, this central magic of science work? The Austrian physicist Eugene Wigner talked about the unreasonable effectiveness of mathematics in the natural sciences. But I like to put it more crudely. Why does the real universe have a mathematical twin that mimics it in every possible way? I'm going to give a few, well, the short answer is unfortunately nobody knows, but I'm going to give some possible explanations. The first one is that in fact the universe does not have a mathematical twin, that it's a complete illusion. And this idea comes from Stephen Wolfram. Now Stephen Wolfram was born in London. He's an English physicist. He was a bit of an infant prodigy. He was actually publishing papers, physics papers, when he was 15. And he invented the computer language Mathematica, and he's a billionaire and he lives in America. Now, Wolfram says, imagine a drunk person who drops their car keys at midnight. They look for their keys under a streetlight. It's not because that's the most likely place to find the keys, it's because it's the only place they can look. And Wolfram thinks that mathematics illuminates only the bit of the universe that mathematics can illuminate, just like the streetlight. And what most of the universe is doing is something else. Well, what most of the universe is doing is complex things like biology and turbulence. And many physicists, or most physicists, think that the reason that we can't describe these things mathematically is because we simply don't have the mathematical tools, but maybe in the 22nd century or the 23rd century we will have. But Wolfram thinks we will never have the tools because he thinks that what the universe is doing is fundamentally unmathematical. So what does he think it's doing? There's clearly some order. If it's not mathematical equations, then it has to be something else ordered. Well, in the early 1980s, Wolfram bought one of the very first personal computers, an IBM PC. And whereas most people probably used their PC for playing video games, but Wolfram decided to investigate simple computer programs and see what they do. And the simplest computer programs he could think of were things called cellular automata. And his idea was to feed them in with an input and take the output and feed it back in as the input. It's rather like a snake eating its own tail. And he found that in most instances, with most simple computer programs, most cellular automata, the output was exceedingly boring, repetitive and boring. But in a very few instances, there were computer programs that generated infinite complexity, nothing that repeated, infinite novelty. And this was a very striking result, a simple computer program producing infinite complexity. So Wolfram thought to himself, is this what nature is doing? Is it, is this the secret of a rose or a newborn baby or a galaxy? Are all these things being generated by simple computer programs? So his idea is that the universe is being generated by a computer program. And it turns out that the only way to find out the outcome of that computer program is to run it to its finish. So the universe is 13.82 billion years old, but in order to know the outcome, in order to predict what we see all around us, you have to run the program for 13.82 billion years. There are no shortcuts. However, it turns out that there are islands within this giant computation where it is possible to predict the outcome at the outset, where there are shortcuts, and these shortcuts are mathematical physics. So in his view, we've actually found the island of predictability in this unpredictable calculation. But most physicists don't believe this. Most physicists believe that the central magic of science needs an explanation. I mean, Paul Dirac, the English physicist, he often said metaphorically, God is a mathematician. So why is the universe mathematical? Why does the central magic of science work? So a person with an interesting idea is the Swedish-American physicist Max Tegmark. And his idea has to do with multiple universes. Now, in the last few decades, it appears that nature has been banging us over the head and from many different directions telling us that there is more than one universe. And now these different multiverses, as they're called, come in different flavours. So, for instance, there are multiverses with different physics in each universe. There are multiverses with the same physics, but maybe different strengths of the force of gravity or different masses for the electron. There are universes with different dimensions. That comes from string theory. So nobody knows how any of these ideas mesh together because it's an emerging paradigm. So this is the basis of his idea. The second component of his idea is that mathematics is physics. Okay, so wherever mathematics is actualized as physics everywhere. So it's a very trivial explanation of why the universe is mathematical, because mathematics and physics are the same thing. So put these two pieces together. What Tegmark thinks is there are an infinity of universes, and in each of these universes there is a piece of mathematics. So in many of the universes, the mathematics is simple. So, for instance, there's the mathematics of, say, flat paper geometry, what we call Euclidean geometry. In other universes, there's maybe the mathematics of logic, what we call Boolean algebra. But in these universes, the mathematics is too simple to produce anything interesting. However, in a handful of universes in this multiverse, the mathematics is complex enough to create galaxies and people and intelligent life. And those universes are described by what we would call the theory of everything. We don't yet know it, but we call it the theory of everything. And it's no accident, of course, that we live in the universe where the mathematics is complex enough to create us. So that's a weird and wonderful explanation. But there is another type of multiverse which is kind of off of on a tangent, but it gives me a convenient way to end this talk. And it's the Many-Worlds Multiverse, in which all possible histories are played out. So, for instance, in fact, an infinite number of times. So, for instance, there's an infinite number of universes where you didn't listen to this talk today and you did something more interesting, or copies of you didn't listen to it and you did something more interesting. There are an infinite number of universes where Donald Trump did not become President of the United States and Boris Johnson did not become Prime Minister of Britain. And there are an infinite number of universes where the dinosaurs were not wiped out by an asteroid 66 million years ago, but developed intelligence and went on to invent motor cars. Why do I like this idea of the multiverse? Well, even if this is the dullest, most boring, most tedious talk you've ever had the misfortune to listen to, I can console myself that in an infinite number of other universes, you thought it was the most interesting talk you'd ever been to, and you bought copies of my book for all of your friends. Thank you very much.